Alright, so now we're finally done this. Let's continue to problem 18. Again, 18 of total 26 problems, and then including example that we already did. So starting with the vertices P1, which is 0, 1, and P2 is 1, 1, P3 is 1, 0, and P4 is 0, 0. Yeah, of a square, we construct further points as shown in the figure. So we'll have this figure here. So we'll have P5 is endpoint. So notice here, P4 is at the 0, 0. So this is 0, 0, and so on. P3 is at 1, 0, and so on. And then P5 is the midpoint of P1, 2. So this one's going to be at 0.5 or 1 over 2. Yeah, 0.5 and 1, and so on. And then P6 is the midpoint of P2 and P3. So P6 is over here. That is at 1 and 1/2. Then P7, notice how P7 is here. This is at 1/2 and 0. So vertical axis is 0, horizontal is 1/2. So yes, and notice how it keeps going in between each half. So this one goes in between these, and then this 9 goes in between. So it always it cuts into the half, and it keeps zigzagging all the way across in a perfect spiral, in a jagged spiral. And we're asked, yeah, so P7 has been midpoint of P3, 4. So P7 is the midpoint of P3, 4. Yeah, P6, P2, 3, and so on. And we're asked here, so the polygonal spiral P1, P2, P3, P4, P5, P6, P7, etc. approaches a point P, so it's approaching a point P inside. And we're asked if the coordinates of Pn are at the nth P are x and yn, show that 1/2 xn plus x sub n plus 1, and then xn plus 2 plus xn plus 3 is all equal to 2, and find a similar equation for the y coordinates. And then we're asked find the coordinates of P, so basically as the limit goes to infinity, which is quite an interesting problem here. All right, so let's continue on to the solution. So solution to part A. So part A says if the coordinates of Pn are xn, yn, and then we're asked to show that 1/2 xn plus 1 plus xn plus 2 plus xn plus 3 is equal to 2, and also find a similar equation for y coordinates. So since Pn is defined as the midpoint of Pn minus 4 and Pn minus 3, or that line right there, we have, so yeah, notice here. So if we have Pn, so if, for example, P5 is the midpoint between P1 and P2. So in other words, this one right here is, if this is n is 5, this equals to 5 minus 4, and this equals 5 minus 3, which equals to 2 there. And then P6 is the midpoint of 2 and 3. So we just increment those. This equals to 6 minus 3. And this over here is equal to 6 minus 2. 6 minus 2. Actually, not 6 minus 2, 6 minus 4. So they're all 6 minus 4, 6 minus 3. And then P7. So P7 is between P3 and P4. This equals to 7 minus 4. 7 minus 4, yeah, 7 minus 4. And this 4 is equal to 7 minus 3. So it's always a minus 3 or minus 4. Yes, so we have Pn is defined as midpoint of Pn minus 4 and Pn minus 3. Yeah, so we have, well, for n equals to 5, we get P5 minus 4, and then P5 minus 3 is equal to P1, P2, etc. And this, it keeps going on for the other one. All right, so what we have here now, so that's what we have for P5, or for n is equal to 5. And then if we were to draw this out in a square, and we could write a formula for xn. You have particular x5. So let's say we have this. All right, so we have this, and this is right here. This is our P4, is at 0, 0. P3 equals to 1, 0. And then P2 equals to 1, 1, and then P1 is equal to 0, 1. And our P5 is going to be right here. This is our P5. P5 is right there. And again, our P5, this is just going to be at 1/2 and 1. And so what we have for the xn position, xn is equal to 1/2 of xn. So we take the coordinates here. So what we'll do is we'll take this right here plus this divided by 2. So basically the average distance from 0 to 1. Yeah, so this is the xn of this coordinates, or the pnth coordinates, or the xn coordinates, or just for the n spot. Yeah, for pn. So then we'll have the xn coordinates 1/2 times by, this is xn minus 4 plus xn minus 3 divided by 2. So in other words, the average. And this is all for n is greater than or equal to 5, because there's only halfway points beyond the square. And also note that for n equals to 5, we get x5 equals to 1/2 times by xn minus 4, which is x1 plus xn5 minus 3 is x2, which again, this equals to 1/2 0, so that's a 0 right here, and then 1 plus 1. So in other words, we just get it 1/2. Alright, so then this just equals to 1/2, as we already had in between here. So like that, that's just our 1/2 right there. And here I just wanted to illustrate that was the halfway point, and there's our 1/2 right there. Alright, so moving forward, we could actually use mathematical induction. So using induction, we can prove this equation that we were asked to solve. So we could prove that. So so we can prove that 1/2 xn plus xn plus 1 plus xn plus 2 plus xn plus 3 equals to 2. So we could prove this. Alright, so in induction, first we have to consider the first case. So let's look at n equals 1. So the case n equals 1 is immediate. We can just plug that inside. So what we'll get is, so for n equals 1, we have 1/2. So xn is x1 plus x2 plus x3, and then plus x4 equals 2. Well, let's solve this and move this down here. Yeah, this equals to, well, let's move it over here to have some more space. x1 is 0. And then x2 is 1. So x2 and x3 are 1. So what we get is 1 plus 1, and x4 is 0. x4 is right here. So what we get is equals 2. This becomes 2, 1/2 plus 2. So times by common denominator, 2/2. This equals 2. Let's put it over here. We're actually, no, I think we're getting ahead of ourselves. This is 0. So this just equals to 2. Yeah, so 1 plus 1. So yeah, there's a 0 there. That's just 0. So this just equals 2, 2. So that is true. So the first case is true. Alright, so let's assume that the result holds for n equals k minus 1. I'll just put a check mark as that's indicating it's true. So this equals to 2 there. So, and then solve for the case n equals k. So what we'll do is we will assume that, we will assume that for k minus 1, so 1/2 of x, k minus 1 plus, this is going to be, yeah, that's k minus 1, that's n there. This is going to be plus 1, so this is k plus x, this will be plus 2, so this is k plus 1. And then plus k plus 2 equals to 2. So assume it's true for that. Again, as per mathematical induction that we went over earlier in the earlier problem. Alright, so if we assume it's true, then for n equals to k, so that was k minus 1. So notice this n plus 3, Yeah, when k is k minus 1, we'll just subtract that, so that's k plus 2. So for n equals to k, we have 1/2 x to the k. Oops, this is x, not k. This is x. So n is k, then plus 1, plus 2, plus 3. And then this is going to be, the next one is k plus 1 plus k plus 2 plus k plus 3 equals 2. Then we got to solve this one. Like this, plus 3. Alright, so we want to solve this, and this is a pretty next level solution that the solutions manual gives. So what it does is, well, it considers this right here. It says k plus 3. It doesn't show up into this assumed equation, but it shows up once here. So it doesn't show up this one, but these ones, well, yeah, all these ones do. K plus 1, k plus 2, and k, but not k1, k minus 1 there. So what it does is it does this. So it takes this assumed one, so we start off here, and it replaces, yeah, so it replaces, or I'll just say replace, because I'm doing the solutions right here. So replace k with k plus 3 minus 3. So we're not changing, well, we are changing this one. We're starting from k there. So it's saying write this out. So then what we get is 1/2 x, and then k plus 3 minus 1, that becomes minus 4, plus x to the k, which is k plus 3 minus 3. And actually, the solutions manual doesn't even explain this. They just they mention this, but they don't actually do it. They just skip all the steps and then go straight ahead to the pretty much the answer. So I am doing this. Well, I'm assuming this is what they were talking about. So then the next one is plus k plus 3. So k plus 3 minus 2, and then there's a plus 2 there. So then this will be plus kx, k plus 3 minus 1 equals to 2, like that. Alright, so if you see the pattern here, and then it does this again. So we'll call this equation 1. And then what you could do is, because notice the pattern here, and then when we could subtract and get a whole bunch of cancellations. If we do another step here, replace k with k plus 3 minus 2. Remember, it will just be shifted by 1. And when we do this, we're basically adding another one. This will end up with a k plus 3 here. This is a k plus 3 minus 1. So what we get is equation 2, 1/2 x, k plus 3, and then there's a minus 1 there. So there's a minus 1, that becomes minus 3, like that. Plus x, k plus 3 minus then it becomes plus 1. This just becomes k, So plus 3 minus 2. And the next one's going to be plus 1. X, k plus 3 minus 1, because we're adding 1 here. And then finally we get a x, k plus 3 plus 2. So then plus 2, then we're left with this. So notice this k over here, x, k plus 3. Now we have this right here. So what we'll do is, so now subtract. So we're going to subtract the 2, subtract both equations like this. And yeah, we could have started from the other one. If we did this one first, we'll subtract that from the other one, or the other one from it. But we'll just do it this way. So what we're going to do is subtract equations 2 minus 1, so that we're left with this k, this x, k plus 3. So we have this term there. So what we'll get is, so when we subtract them all, so with this minus this, we'll see what we have. So this right here, this is 1/2. This lines up with this, that's 1. So we're subtracting that. That's going to be equals to negative 1/2 x, k plus 3 minus 3. And then the next one here, so we have this k plus 3 minus 2. that is, well, this right here. So this will cancel. So we'll just cancel this out. Yeah, so that just cancels. And then the next one is right here, x k plus 3 minus 1. So we have one here. This also cancels. And then we're left with, well, this right here, x k plus 3. Well, actually, before we get to that, well, we have this one here. So we have this, and we have this right here, but we're subtracting that. So we'll just subtract it. 1/2 x k plus 3 minus 4, and then plus this. Plus x k plus 3, and then 2 minus 2 is just 0, like that. And now what we'll do is we'll move these over to the other side and factor out the 1/2, and what we get is x, and then solve for this one by itself. So x k plus 3 is equal to 1/2. Factor that out. These are going to be additions now, and we're going to be adding x k plus 3 minus 3, like this. Okay, yeah, minus 3. Or we'll do this one. We'll do this one in front, actually. Yeah, just so the numbers get bigger. So this is minus 3. So we'll do this one first. Minus 4 plus x k plus 3 minus 3. And then if we solve this out, or just simplify this. This becomes 1/2 x k minus 1. So 3 minus 4 is 1. And then this one is going to be plus xk. Plus xk, like that. So this is the equation for xk plus 3. Alright, so now that we have this, what we can do is, well, let's go start off with our case n equals k right here. So we have this 1/2 xk plus xk plus 1, then plus xk plus 2, then plus xk plus 3. And then we could insert this inside it. So thus we get 1/2 xk plus xk plus 1 plus xk plus 2 plus xk plus 3, and we're going to throw this inside there. This equals to 1/2 xk plus xk plus 1 plus xk plus 2 plus 1/2, and then 1/2, and then we just get our xk minus 1 plus xk. I'll move this here, plus xk, like that. Alright, so I just moved it over here so it fits all into this column. So we have this, and now if we expand this out, we get, and I'm going to move the smallest term on this side. So this equals to 1/2 xk minus 1, and then now we have a 1/2 xk right here. So I just move this over to here, and now this plus this 1/2 xk. Well, I'll just add it just for completeness. 1/2 xk plus 1/2 xk, and then plus xk plus 1 plus xk plus 2, like that. This equals to 1/2 xk minus 1, and now these add up, plus yeah, this just becomes 1, so xk, and then plus xk plus 1 plus xk plus 2. So in other words, this right here, this is the case, yeah, this is a case of, yeah, case n equals to k minus 1. So that's k minus 1. Look, that's exactly what we assumed. This right here. So that equals to 2 then. So in other words, this whole thing equals to 2. And we have just proved it. So then this equals to 2. And that's check mark. Because this is the case for n equals k minus 1, which we assumed is true. And then the k version, or the case for n equals k, is also true. So hence we proved by induction. All right. Yeah, so thus our induction is true. And I'll make some room for it. Yeah, so the our induction hypothesis is true, and similarly the same argument holds true for y, except 2 is replaced by, yeah, so we can do the exact same steps, but we're going to replace this 2 by, well, we're going to take that same equation, so this right here, 1/2 xn plus xn plus 1 plus xn plus 2 plus xn plus 3, and then instead of 2, we're going to solve for what it should be. So I'll write for n is greater than or equal to 5, and then yn is also going to be the average. So yn is equal to 1/2, again, just going to be 1/2 yn minus 4 plus yn minus 3. So exactly the same thing, because it's a square. Remember, it's a square. So then we look at case for case n equals to, or yeah, for case, instead of 4, for case, the first case, n equals to 1, we get 1/2 y1 plus y2. Remember, k plus 1, yeah, so that's k plus 1, k plus 2, or n. So this one is going to be for n equals 1. So for n equals 1, and yeah, for next one's n, for n equals 1 there. So y1, then it's going to be n plus 1. Yeah, so we're going to go over here. So n plus 1 plus 2 plus 3. So then this becomes plus 3 plus the next one is y4. This equals 2. Well, let's look at our square. So y1 is 1. So the y1 and y2 are 1, and y3 and y4 are 0. So there's 0, the y coordinates. This is 1, 1, and 0, 0. So we could just throw this inside. So this 1/2, this becomes 1/2 times 1 plus y2 is also 1. Then y3 is 0. Plus y4 is 0. So this becomes, this becomes 1/2 plus 1. In other words, multiplied by top and bottom by 2. So we get a 2 plus 1 is 3 over 2. So if case 1 is, case for n equals 1 is true, and then we could do the same thing by induction, and then it's true for all of them. Exactly the same thing. The only difference is that constant number. Instead of 3 over 2, instead of the other one was 2, we get 3 over 2. Alright, so thus we have, so put it all together, thus 1/2 yn plus yn plus 1 plus yn plus 2 plus yn plus 3 equals to 3 over 2. And we can bold all this, or circle this whole thing like this. Alright, so now that we have this, and also I just want to put a note for all n. This is basically for all integers, n is greater than or equal to 1. Like there, because it applies for 1, 2, 3, etc. Alright, so we have this. Now let's look at the solution to question B. And if we scroll up to question B, this states, find the coordinates of P. So in other words, when n approaches infinity. Alright, so, well, to solve this, it's actually fairly straightforward. So we are asked to find the coordinates of P, not Pn. So in other words, the coordinates of P, and then basically we can take the following limit and solve for xn. So in other words, the coordinates of P are the limit as, well, we can just write this, the coordinates of P are the limit as n approaches infinity of Pn, just the nth P, which are xn and then yn. So in other words, we can solve for this by taking the limit there, and we have equations for xn and yn. So we have this equation for yn, and we have it for xn, this setup here. Let's go back to the full equation. So we have it for this right here, 1/2 xn plus 1 all the way there equals to 2. So what we'll do is, and it equals to 2, so then if we take the limit, that has to equal to 2, because it's already, because it's equal to 2. So we could do a limit as n approaches infinity of 1/2 xn plus xn plus 1 plus xn plus 2 plus xn plus 3. This equals to 2. So we know the limit is 2 because all that equals to 2. So we could do, now we use our limit rules and write this all as separate limits. Limit as n approaches infinity of 1/2 xn. I'll just take this x, I'll take the 1/2 out. 1/2 limit as n approaches infinity of xn plus limit as n approaches infinity of xn plus 1 plus limit as n approaches infinity of xn plus 2, and then we get plus limit as n approaches infinity of xn plus 3, and again, all this is equal to, but that's pretty straightforward. So that all equals 2, but then these are all the same limit. So as xn goes to infinity, sub infinity, they're all approaching the same one, because once you're going to infinity, the n plus infinity plus 1 is still infinity, and this one plus infinity is still infinity. So in other words, all of this, these are all the same limits. All the same limits. This means then that, this means that we could factor out xn from all of them. They're all the same limits, so it's the same thing as writing, well, just factoring it all out, same thing as writing 1/2 plus 1 plus 1. So we have 1/2, just factor out everything, and this will be 1, 1, 1, plus 1, another 1, and then times it by the limit of just one of them, and we'll just take the first one. Limit as xn approaches, as n approaches infinity of xn. So this is equal to 2, and then this right here, 1/2, this is going to be, well, 1/2 plus 3, and we can multiply top and bottom by 3 over 3. Actually, no, we don't multiply that. We multiply this by 2 over 2. So that's the same common denominator, and then that becomes, well, 6 plus 1 is 7. 7 over 2. So then this becomes equals to 7 over 2 limit as n approaches infinity of xn, which equals all to 2. So then we can move this over to this side. So in other words, what we get is limit as n approaches infinity of xn is equal to, so 2 times 2 is 4, so we get 4 over 7, which is quite fascinating. So that is 4 over 7. And then similarly, we could do the same thing for the y, but instead of it equaling to 2, similarly, we could do this for, similarly for the y, it's going to be the exact same thing, but instead of this equaling to 2, we're going to get, so similarly, we're going to get, I'll just leave it like that. Similarly, we'll get a we'll just have a 7 over 2 limit as n approaches infinity, because remember, it's the exact same thing, but it equals to a different number. Instead of 2, it equals to 3 over 2 of yn, this is n, not 2, yn, so make sure I got it all right, yes, yn equals to 3 over 2. So that's the only difference, 3 over 2, and then we divide this out, well, this cancels, so move this over, the 2's cancel, we'll have 3 over 2, so then we get limit as n approaches infinity of yn is equal to 3 over 7. So yes, so that's what we get. Yeah, so then this means, then, let's put it all together, thus, limit as n approaches infinity of Pn, which is xn, yn, is equal to P, and it equals to 4 over 7 over 3 over 7, which is quite fascinating. So those are the coordinates of P.